Hello again, YouTube. Before I move on to other things, I just want to deal with it's a nice logical step from RS232. I suppose we generally call them serial interfaces, serial communications channels. The last time I dealt with this Maxim 3221, I think it is, which is an RS232 transceiver that converts our 3v3 from the microcontroller into a higher voltage, so a 12 volts on this ground receive transmit receive, sorry, ground receive transmit receive. So basically we've got our standard serial protocol coming in on D3 on this little board, and then the RS232 transceiver converts anything on the transmit line into a 12 volt RS232, and then anything it receives on the receive line, 12 volts, it drops that down to 3v3 for our microcontroller, so that we don't blow up a microcontroller with 12 volt serial. And I looped the two wires back together, the transmit and receive, so that we could just test a loop back. So in a similar way, this board features a different transceiver. This is an RS485 transceiver. So basically the same thing is happening on this. In this time at pin D0, we're transmitting out 3v3 serial communications waveform, and this transceiver RS485 is converting that into an RS485 signal on, again, 3 pins, but this time we don't have a transmit and receive. We have an A, I've got ground in the middle, and B. And if I go to the actual device, is this Texas Instruments SN65HVD72D. So for the purposes of this video, I shall just call it the RS485 transceiver. So we started with RS232 and serial communications, and we had a date for that of 1960 when it was first introduced. Now that I should have mentioned, I probably didn't mention at the time, that when our circuit is transmitting as 0, the voltage is high. So it idles to a high voltage, and the standard expects it to be up quite high, so the voltage difference between the two is 3v3. That's why we had a transceiver the last time, to bump up that voltage, so we were sure that it would be, like I said, some devices expect that high voltage. So when there's a 0, a space, communications is sometimes talks about marking space. So if there's a space, the 0 logic, it's a high voltage. It's kind of reverse of what you'd expect. So that was our 232. 485. And the other thing about this, sorry, I should say, this is a full duplex protocol, and that because there's a dedicated transmit line, can see it on this board, there's a dedicated transmit and a dedicated receive. So both, we can receive and transmit at the same time. The problem with it is that it's full duplex, it can receive and transmit at the same time, but it can only transmit and receive between 2 devices. So it's a point-to-point protocol. It's also, because of its voltage arrangement, it's susceptible to electronic noise on the line. So if we were looking at the signal line and I turned off a kettle or something, or some electronic device, then there might be a voltage spike, and that would cause a spike on that serial line, and that would be interpreted as a start bit, and then the computer would probably read that as a start bit, or the device would read that as a start bit, and assume that that was a transmission of a data byte, which was 00. The 485 doesn't have a transmit and receive. It has 2 lines, which are A and B in RS485, and that's what our transceiver is doing. It is converting our serial signal into RS485's A and B. So in this case, the two voltages, it's called differential signaling, and it's over a twisted pair. Now, most protocols that I can think of leading on from this would use differential signaling because it's less susceptible to electronic noise on the line. We could do an experiment with that, but I'll leave that for the minute. So CAN bus, RS485, Ethernet, even Ethernet. When you open an Ethernet, a Cat5 cable, you've got loads. You've got four or five different twisted pairs, and they're using exactly the same differential signaling because of it's more tolerant of noise. It's immune to that electronic noise on the line. So normally we have the two lines and we've got a voltage divider. I haven't got that in this case, so I've just connected it straight to my oscilloscope and just to show you the output. But normally there is a voltage divider which suppresses noise again and biases things up. So the transceiver converts what it receives, what we're transmitting it, which is a little serial test, 4-letter four ASCII characters with the word test. Now the transceiver will convert that into these A and B voltages. So if it's a logic low, if it's a logic 0, then A is low, B is high. For logic 1, it's the other way around. So the two voltages switch. So you can see it in a diagram down here. In the idle case, the two lines, the voltages on those two lines are set by that resistor divider network. So in the idle case, the two voltages just settle down to these voltages. And then when something decides to drive the line, then we get the differential signal between the two. So either one is positive with respect to the other, or the other is positive with respect to the other. So, and that's basically it. So that little board I mentioned I've changed the code, and instead of having me typing code, I've just typed it and I'll commit it back up to the Git repository. So previously our code was working on an RS232 transceiver. We were transmitting a little test message with the word test, and we were doing that periodically on a timer. So now, instead of having our transmit pin for the maxim on RD3, we've basically got our transmit pin on RD0. We've got a receive pin again, but we've only got one control pin, and that is to enable the transmission. I said that RS232 has a dedicated receive and a dedicated transmit. This A and B is not dedicated to either transmit or receive, it's both. So in the idle state, when the two voltages settle back, if nobody is driving the line, then you're listening. So everything is listening. And that's the other point about this. It's RS232 is point to point. This can have several devices on the line. It's usually a master and a number of slaves. But the master can send out a message and say, asking for one of the other devices connected to the line, the RS485 line, to respond, and then it will go back to the idle state with the voltage divider setting the voltage on the line, and then wait for a response. So this is half duplex. The master will send and then wait to receive. But we can't do both at the same time. So in the chip there are, and that's the arrangement of an RS485 bus. So in the chip there are a number of, it's a very small chip. There's the A and B going to the line, there's the VCC and ground, and then there's a received data and the data that we're driving out. And this pin 2 and 3, if DE is high, then we're transmitting. If RE is low, then we're receiving. So I've just, in that little board, I've tied the two lines together so that in the code, when I want to send, I drive the line high, the GPIO line high, and when I want to receive, I just drive the GPI low. And that goes out on this RD1 pin. And the timer does exactly the same thing, except, well, I'll go down to the main. Instead of having all these GPIO pins that were for the maxim, we've only got 3. We've got a transmit, receive, and then we've got the pin that decides whether we're transmitting or receiving. So we, in the idle state, we just send this into the receive mode, and it goes back to idle voltage, and it's waiting for somebody on the line to transmit, or it then grabs the line and transmits, which is what we're going to do. We set up exactly the same thing. We've got a TX pin and RX pin going out of the microcontroller. We've also set up, we need to know the transmitter is finished transmitting so that we can drop back out of transmit mode on the RS485 transceiver and start listening for a response. So we set up this callback for the transmitter finished, and that's all the code does. Then our old timer function, instead of just transmitting the test buffer, it now has to tell the RS485 transceiver I want to transmit, so it sets the control line high, then it transmits. When the transmitter is finished, we get the callback and we set the transmitter, the RS485 transceiver, into receive mode, and that's it, job done. And I'll commit this code later today, hopefully, but it's more or less exactly the same, except that we now have to tell the transceiver to go into transmit or receive mode, and we have to know when the transmitter's finished to do that, so we use the callback. So last time I fought with Bitscope, which didn't agree with me, and this time I'm using a Rigol, but the Rigol only has a PC interface on Windows, so I'm using a Windows virtual machine, and we shall use their Ultrascope. And so the code does exactly the same thing as it did. It sends out a test message periodically. So that's our RS. It's not strictly RS232, but it's a serial RS232, like it's only 3v3. And that's our serial communications. So in the idle state, the voltage is high, that's a 0 on the line, a logical 0. And then when it drops down to 0 volts, that's a logical 1. And that's dropping down is the start bit as well. So that's telling that whoever's listening on the line, we've got a start bit. So if that's the serial. Now A, if we look at A, you can see that when this is a logical 1 or 0, sorry, it's a high voltage. Before we grab the receiver, look, the RS485 transceiver's in the idle mode there. It's listening for something. But we then grab the transmit, say we're going to transmit, and it then drives the line high on A because we're transmitting an idle, which is logic 0, which is a high voltage. And that's the two combined. Wait for it to trigger again. And then you can see the differential signal. So all our RS485 transceiver is doing is monitoring the input and then just setting A and B accordingly. And once we're finished, we drop the line. We tell the RS485 transceiver we're finished transmitting, and the two voltages. Now if the biasing resistors were there, this drop would be very different, but it just, the two voltages return to their idle condition. We're finished transmitting. And like I say, most protocols now use that, apart from Linbus is one I can think of that doesn't, but most protocols use this because if we have a voltage spike on this serial line, then we interpret that as, we can potentially interpret that as a start bit, and then we received a byte of data that was never transmitted. Whereas in this, because we're measuring the difference between two lines, and a voltage spike will affect both the same, if both these voltages shoot up the same, so if both shoot up by 2 volts, that's very low voltage, but if both of these shoot up a small voltage, the difference between them is still going to be the same difference. So it's less susceptible to noise. And that's the reason why it's used in all these protocols. And if you look at the actual board, most of this is TVS, transient voltage suppression. So because RS485 goes into a lot of industrial noisy environments where there is a lot of electrical noise, and you will get voltage spikes, we know we're going to get voltage spikes, or we expect them, then we've got transient voltage suppressors built into our circuit and varistors to try and minimize both on the A and the B channel. A is on top, B is on the bottom, but both those channels we're trying to suppress the noise on them, and then it's fed into our transceiver. And that's it. That's RS485. Now there's a few others, RS422, but that was the start of this differential signaling, and I thought I'd better mention it when I was leading from like RS232 and strict serial, where you've got just one line transmit, one line receive to this differential signal, because most protocols now that we're going to look at are going to use this differential signaling in one form or another. And that's it for this video. I hope that's of use to some people. It's a very simple code change. I'll commit it later on, and yeah, read through the Wikipedia article on RS485. It's not as difficult as you might think. It's just a move from one voltage line to a differential signal, and that's the main difference. Thanks a million for watching, and see you again next time.